How's it going, everybody? In this video, I wanted to continue our Let's Talk About Networking series by taking a lot of the feedback I got from the previous video about campus network design, which I'm really happy that a lot of people watched the video in at least the last portion of it. I'm always worried if people get to the end of the video, so I'm thankful that people actually get to the end of the video. And so taking the feedback that I received from everyone, ta-da! Here's our topology. So this will be a comprehensive look. I know there's a lot of LAN configuration, which will give us a lot of flexibility in terms of how we go about getting things configured and things like that. I want to spend a couple minutes just kind of going over the high-level details, and then we're going to dive right into some of the design aspects of things. So I was doing some brainstorming as I was trying to figure out how I was going to approach this, because I actually don't have a workflow, if you will, because it was like, where do I insert design into Encore and an RC and then eventually SD-WAN? So I figured, you know what? Let's talk about the design aspects of things first, lay out the high-level details, try to help you understand what exactly is happening with a particular topic, and then focus on the actual implementation. So the design section will actually be kind of fragmented throughout the entire set of videos. So I'll cover the design aspect of things first, and then we'll dive into the individual configuration details, how to get it working, how to verify it, if there's, if we run into issues, what steps to troubleshoot, things like that. So that's my goal, is to help you not just talk about a particular technology and say, okay, this is how OSPF works, this is how multi-area configuration works, this is what LSAs are. That's still necessary information, but I want to take it a couple steps further and go, okay, if you have a specific design, let's say you talk about, and this topology is big enough to where we can play around with a couple different variations of that, and we can see what those details would look like. So with that being said, that's basically where we are at in terms of the flow. So design will be kind of broken up across the entire Encore and RC sections because of the fact of what that, because the design ties to the config ties to the design. So I want to kind of separate it that way. So basically the idea is we look at the addressing pieces here. We're going to start from the bottom, start from the top and work our way down. So we have IPv4 and IPv6. We're going to start off with addressing. So for those of you that are coming from a CCNA level and you're working your way up, maybe you already have a CCNP, or maybe you take an exam and you want to dive into it a little bit deeper, or you're studying for a new test, whatever the case might be, whatever your reasons are. My goal is to just talk about the technology in general, and then you can figure out on your own, okay, I've talked about, Rob went over this, so I know that I'm good to go here. So that's basically where I'm going with this. I'm also going to have some other of these series, so let's talk about security, let's talk about data center, and stuff like that as I progress forward, because those are other areas that I want to dive into. So we're going to start with addressing, and then we'll talk about the different dynamic routing protocols and how they all work and stuff like that. Then we'll talk about migration strategies, deal with the different types of tunneling and stuff like that. Then we've already kind of talked about this a little bit already with the campus network for high availability. We talked about the different components, right? Core distribution access. We'll go into much more detail than that. And then we'll dive into the SD access and the SD-WAN aspects of things. Then we have the WAN. We'll talk about the different WAN capabilities. We're going to be spending quite a bit of time in this portion of WAN. When we cover a particular topic, we'll dive into those details. We will be doing DMVPN. We will be doing MPLS Layer 3 VPNs. We will be taking a look at IPsec VPNs. We'll be taking a look at Flex VPN. We'll take a look at Get VPN. We'll take a look at a lot of different capabilities, because at the end of the day, it's really useful to have the understanding and know what to do with it. So we'll cover the topic anyway, even though we're not going to necessarily have to configure it, or you won't be technically tested on it, but it's a topic here. And it's like, well, I'm familiar with all of these, so we'll be able to take a look at how all of that stuff works. And then we'll take a look at single-homed, multi-homed, and all that type of stuff, and how you can do backup connectivity. We'll take a look at those details as well. Obviously SD-WAN. It doesn't, here it's more or less just the high level details to it, but when we go through the SD-WAN pieces, we'll cover that as well. Network services, we're definitely going to take a look at, it's got a big thing with QoS. We'll spend some time on quality of service. and deal with, what's classification and marking, shaping, policing, and queuing. We'll take a look at how those details come into play. And then we will dive into network management. What's the difference between in-band and out-of-band? And then segmented management networks and things like that. And then automation. I'm not going to spend much time in this area because it's not an area of expertise for me. I am still learning this, but I'm not actively learning it. It's like one of those things where it's like, well, eventually I will dive into this. So that's basically where we are in terms of those details. So going back to our topology, let's talk about addressing. So for those of you that are paying attention to the addressing scheme, you can see that I've got some addressing done. And the reason why I have this addressing done is because these connections between the core switches, so CSW 1, 2, 3, and 4, and distribution 7 through 14, or I should say 5 through 14, excuse me, these are going to be layer 3 connections, okay? And the core switches are going to be what we connect into for integrating between all the different modules. So, for example, and I don't have any one of these specifically labeled as of right now, but for example, this could be the LAN segment or a LAN module. And then up here, this could be the data center. This could be the DMZ. We have a number of different capabilities that we could throw at this and test out. Then we have the internet module, and then we have the WAN module. So we have a lot of different capabilities and things like that we'll take a look at in terms of how does this work design-wise, how would we configure a particular topic and things like that. I've also have a couple of ASAs in here to play around with some VPN technologies because, at the end of the day, the likelihood of you having to VPN into a branch office and then jump across the WAN to go back to the HQ is highly unlikely. You're either going to be connecting to a data center VPN, so like you throw up an ASA firewall into a data center and then people VPN into that, or you have a dedicated pipe that people are going to VPN in over, and that will be your VPN connection. And then from there, you'll be able to go wherever you need to. So for example, when I spin up Win10 and he needs to VPN into ASA22, and he needs to, for example, telnet into R26, he'll actually flow through the MPLS WAN or go over DMVPN. And we'll talk about those details when we get there. But I want to give you some high-level details as to how that would actually come into play, why you would want to do something like that, so on and so forth. Because it's actually very, very commonly deployed where you allow, like I was a consultant for a really, really long time. I still do quite a bit of design consulting as well. And a lot of times I'm coming up with architectures like this and I'm saying, okay, this is what we should do. And this is why we should segment it the way we need it to, because this provides you a lot of high availability, right? Not only is it redundant, it's also highly resilient. But if you put in the right routing protocol, and what's the right routing protocol? It really depends on what the customer wants. So that's one of the things that I'll talk about in more detail later. But basically what I want you to take away from that statement is it's not a discussion of, hey, I'm a fan of EIGRP but not OSPF because of X. Or the next person says, I like OSPF over EIGRP because of X. Well, it's not a like or dislike. It's know them all, right? Know them all, know them well. And then that's just another tool in your tool belt that customer N comes to you and says, hey, we want to do X, Y, Z. What do is there a solution for that? And you might be like, well, could we do this and we can add that feature in or whatever the case might be. So then it's like a mechanic that's trying to troubleshoot the transmission. They have a tool that helps them troubleshoot the transmission. So there's, as long as you have the right tools in your tool belt, it makes you that much more flexible in the environment. That's what we really want to be able to convey here. So with that being said, let's take a look at the addressing. I'm going to actually pause the video and I'm going to bring this down a little bit so we have a place where we can whiteboard, because I'm going to start talking about the basically just the high level details of IP addressing. I'm not going to go into the weeds really, if I don't need to, but yeah, I'll talk about that in more detail. Okay, the first thing that I want to dive into is more or less just some of the fundamentals that we need to know about when it comes to IP addressing, because that's really, really important that you have IP addressing down in those terms. We go ahead and get out of the way. So when it comes to IP addressing, we have a couple different classes that we want to talk about. You have A, B, and you have C, right? A is going to be basically 1.000. Let me put dots in here. Through, and this is going to be 126.255.255.255, right? We're going to omit the 127 range because that's for loopbacks. Then up here we have, for class B, we have 128.0.0.0 through 191.255.255.255, right? And then class C is going to be your 192 through your 223.255.255.255. All right, if you didn't already know that, there you go. Now, there's addresses in here that we can use for private addressing. So when I use the term RFC 1918, this is IPv4 private addresses. Now, those ranges are 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16, right? Those are our address ranges. So what this gives me, when we take a look at this from an addressing perspective, we need to understand first octet, second octet, third octet, fourth octet. Okay? So in other words, what this basically does, if you take this 10 and you've got /8, which means the 9th through 32nd bits are allocatable to hosts, right? That's basically what this means. So in other words, if I was to get a scenario where a individual comes to me and says, hey Rob, I need to allocate an address block to a group of users of 3,000. I'm like, okay, that's a big site. 3,000 people? That's a huge site, more like a campus. So what would I do for that? For 3,000 users? Well, this is where knowing how to subnet becomes extremely useful. So how do you subnet? Well, subnetting in and of itself is actually not that complicated. So I'm going to show you how when I go into a Cisco exam, when I was taking a CCNA and CCNP, I didn't really have to do it on CCIE at all. I wrote it down because all of my CCIEs, my written exams, I've been, there's really not a lot of addressing on those, and not really even CCNP really. CCNA was heavy in addressing, which it needs to be because it's an associate level exam. So let's go ahead and talk about the IP addressing aspect of it first. When we talk about addressing, in order to figure this out, we need to have subnetting understood. Okay, so if you were to take one of these blocks right here, this octet as it's referred to, an octet in the simplest terms is going to be 8 bits, right? You got 8 bits that you can work with. Now, how the number 10 comes into play, or how the number 192 comes into play, or any other value between 0 and 255, how that comes into play is based off of the numbering scheme that's associated to each one of these bits. So for example, if I was to take, you've got a bit, well, I'm just going to draw a line. We've got 8 of them, right? Let me space that one out just a little bit better. So there's our 8 bits right there. Well, what's going to end up happening is from left to right, not right to left. From left to right, there's going to be a descending order of bits or numbers associated to each one of these bits. They start at 128 and they go down in increments of 2. So 64, 32, 16, 8, 4, 2, 1, right? Well, when you have it set up this way, what you do is, depending on how the architecture set up. So for example, in this case here, you can't really figure this out right now because you have to understand how this plays into it first. I'll talk about this specifically here in just a few minutes because that'll help tie it back together as how these bit ranges work. But in order to understand the octet, we have to understand how the bits are ordered in the octet. So what this means is, when I go from left to right or if I go from right to left, what ends up happening is if you added up all of these numbers together, they're going to equal 255, right? So now if you take this value and if I turn certain bits on and certain bits off, okay, so if I come in here and I turn this bit off and I turn this bit off, what's my number? Well, you can simply take 40 away from 255, right, which is going to leave me 215. 215 isn't an actual number, so what you've actually got to do is you've got to take 128 and you've got to take that 128 and 64 is 192. And then what you do is for every number from there, you just add this number to this value. This would be 224. This would be 240. This is 248. 252. 254. I don't know why I couldn't do the math on that. And then 255. So what you would do is you would take these numbers right here and you would add them together. So 128 and 64 is 192 plus 16. So 192 plus 16 is going to be, this is 8, and this is a 0, and this is a 2, so 208 plus 4 puts us at 212 plus 3 plus puts us at a 215, right? So 215 is going to be the IP address that's going to be associated. Now, let me clean that up a little bit. 215 is going to be the IP address that's allocated, right? So 215, or just like I mentioned a moment ago, you're taking 40 away, so 255 minus 40 would be 215, right? By adding these up, I come to the same conclusion. Whether you subtract from these bits right here, or whether you add them together and remove the ones that didn't get used, you get the same result, right? So what you end up doing here is once these bits are turned on, whichever octet you're building this for, whether it's this one, this one, this one, or this one, then you would take this number right here, this 215, and then you would allocate it to this guy. So for example, if I was to take a situation where somebody had given me a value of 255 or 10.215.27.8, you could take the 27.8 and then you could figure out, okay, what's the binary equivalent for that. So basically what ended up happening is if we were to take the 215 again, right, in binary that would be 1 1 0 1 0 1 1 1. This equals 215, right? So we can know that, and the computers read binary, right? They know how to interpret it. That's how they know what's going on. So we don't have to understand that. We put things in what they refer to as dotted decimal. This is dotted decimal up here, right? So we're putting something into a format that we can understand, where computers read it as binary, ones and zeros. If the bit is on, it's a 1. If the bit is off, it's a 0. You turn the bits on, it becomes something. If you turn the bits off, it becomes something else, right? So 0 is all zeros. A 255 is all ones turned on. And anything in between is a different variation of the bits in the order from left to right turned on or off depending on what the number is going to be. Simple as that. Now, with that being said, the next thing to understand is when we take a look at how this comes into play, there's how you take these the octets and you build them out. I just did one octet, right? So if I was to take these octets and I was to start building them out, you would do the math on each one of these and then you would get to a number. For example, 10.1.62.27. So obviously you're going to have the 8 and the 2 turned on, you're going to have the 1 turned on, you're going to have the 32, 16, 8, 4, whatever it ties out to be, will get you to 62, whatever that combination looks like, and then 27 would be whatever combination it comes up to be, right? So you're able to figure out binary-wise by looking at this number right here and going, okay, how many different bits do I have to turn on or off in order to get this to work? It's just figuring out the combination. So once you figure out the combination, you're good. Okay. Now let's go ahead and take this a step further. Now, once we have the combination figured out, the next thing to figure out is going to be how to correlate the binary digit, the binary number, and its associated number that goes with it. So like you got the 128 is what they refer to as a high order bit. Then you go 64, then you got 32, you got 16, you got 8, 4, 2, oops, and then 1, right? So this would be 255. The inverse of all these would be all turned off, which would be a 0, right? Pretty straightforward stuff. Now, when you go take an exam, one of the things that I always recommend students do is from the /16 to the right to a /30 is write out all these values. So let's work our way. I always like to start from the right and work my way left. It just seems to do the job for me. So if you do a /30, you're going to be having 4 possible hosts, right? That's what this equals here. And then I always write down in the 4th octet what the subnet mask would be. So in this case here would be a 252, right? Let me clean that up a little bit. That's actually a 5. Now if you go to the left and do a /29, this is going to be 8 because it's the next number up. And this will be what? So we're taking from 4, we're going to 8. So this would take us from a 252 to a 248, right? And then you would continue down. So /28 is going to be 16, which would be a .240. And then you would do a /27, this is 32, which would be a, that's 32, which would be a 224. And then you have a /26, this would be a 64, this would be a .192. A /25 would be a 128, which would be a, this here would be a 128, right? So, and then as you're going to the left, you do a /24, this would be 256, which would be a .0. You might be like, well, how does that work? Well, this works, and let me finish this out, and I'll explain to you what how it's working that way. If I do a /23, this is going to be a 512, which is going to be a .254. Okay, and then if we do a /22, this will be a 1024. This will be a .252. Do a /23. I'm sorry, 21. This will be a 2048. And a .248. /20. This will be a 4096. We got 248. The next one is a 240. And then we do a /19. This will be an 8192. This will be a .224. Now, as you continue going left, this is 19. We'll do 18 since we're right here. We're going to do a this will be a 16384 and a .192. And then we do a /17. This will be a 32768. This will be a .128. And then we have a /16. This will be a 65,535. And this will be a .0. Right? So when you get down to the zeros, right here, this one right here, this will be a 255.255.255.0. Okay, this is a class C subnet mask. Down here we have a 255.255.0.0. What I just did was this entire block right here ties to this guy right there. This entire block ties to this guy right here. So when I correlate this, Class C address range always focuses here, Class B always focuses in the third octet. Because I can take these ranges and I can say, okay, based off of what I've got, if remember our value is 3,000, so that's going to be a pretty large campus, right? So if I have a single location that is tied to a 3,000 user campus, then I know that my number is going to fall in between this guy and this guy, right? Well, that's great and all, but let me pose the question. Can I allocate 2048? Would that be enough IP addresses? And the answer would be no, it's not, right? Because it's 1,000 IPs roughly short. So I can go to the 4,096. Would that be enough? Absolutely. You can't. There's no way to custom fit IP addressing without having to take a address range like this guy and this guy. So you could have a /21 and a /22. These would both fill into this address range right here. It would be able to meet the IP addressing requirement, but you'd have two different subnets because each one of these would be a subnet, /21 and /22. You could make it work, although it would be very, very dirty. Your routing design would look a little funny if you were to do that. You'd have a bunch of different address ranges and stuff like that. You wouldn't be able to summarize that into a single advertisement, although there are times when you don't have a choice, right? So I don't want to make it sound like this example here, there's never a use case. Because there's been a few times where I've gone into an organization to do a readdressing scheme, or they're trying to restructure the environment and make things a little more scalable. Maybe they started up with a 192.168 address range, and then they've grown beyond that, and now they need to go 172.16, or maybe they're like, you know what, we're not going to play any games, we're going to just do 10 slats everywhere, and then we're going to start translating one address range into another one, and we start advertising those routes. I have been in those addressing scheme transitions. They are not fun. So if I could ever discourage you from doing that, this would be the time to do that. Don't do that. But you can use another capability by taking the address range above it. This would more than fill the 3,000 IP address requirement, right? So, but that would also give you an additional 1,000 IPs. But Rob, that's a waste of IPs. Yeah, you're right. It is. What can you do about that? Not a lot. Honestly, there's really not much you can do about it. It's either you've done your job and you've got down to the exact amount of IP addresses you need to, or which is hard to do, to be honest with you, or you find out what just about the right size is going to be for you, and then you pick a point. Okay, 3,000 IPs is the range that we want to use. Okay, well, that's kind of funny you want to do that. Could you do the two subnets? So this would be the two subnet, and then this guy right here would be the one subnet allocation. You could do either one. It's up to you on how you want to do it. I discourage the two subnet one. The reason why is because I'd have to advertise two very large address ranges from that location. However, the larger one, the 2,000 IP address range, would be like the initial push, right? And then as soon as those 2,000 IPs get used, you could then transition over to the 1,024 that's left if you need for expansion, right? So that would get you to the 3,000. But what happens if you go above that? What do you do then? Well, could you grab another 1,000 IPs, another /22? Sure, you could, absolutely. But now again, that's three subnets, 1/21 and then 2/22s. Again, your routing scheme is going to start to look a little funny. It might be difficult to do that. You might not be able to, or at least you might not be able to grab what they refer to as contiguous ranges. So for example, if we were to look at this and how it works, the key factor that comes into how this actually plays out is going to be based off of the range that comes into play, which is where I was going with this point, because this is where I see a lot of people make mistakes when they start diving into the details. So let's say we're playing with the 10.0.0.0/8 range, right? And my boss or somebody comes to me and says, okay, we're going to put in a new campus in Detroit. and we decided we're going to have a whole boatload of people working there. I'm like, okay, great. So I don't get into the politics. I don't get into the real estate. I don't really care about any of that. If I need to go deploy a new site, I know what I need to go do. So what I would do is, let's assume no other allocations have been made yet, right? So this is a brand new deployment. We don't have to worry about any other previous addressing requirements. So it means I can grab 10.0 if I want to. So that's what we're going to do. But no, we'll look at it both ways. Okay, so from the one subnet variation, the /20 gives me a range. Just remember that the /20, I'm looking at that as we have a 1, 2, 4, 8, 16, 32, 64, and then a 128, right? These are going to be our binary numbers at the top. Well, when I correlate this, I have the 16 here. The 16 is going to be my range, okay? And the third octet, right? So I'm starting big, and then we'll work our way smaller as we continue. So what that means that for this particular location, I have the ability of doing, let's do the one subnet first, because that'll be easier to subnet first. So we're going to do the 10.0.0.0/20. That's going to be the address range that we allocate, which means that this becomes my range. 16 becomes my range in this octet, which means my next available subnet that I can allocate is going to be 10.0.16.0. Then the following one after that is going to be a 32, and then a 48, then a 64, so on and so forth. So that means for the Detroit location, 10.0.0.0/20 has been allocated, which means in reality, let me go ahead and back this up just a little bit. So I have a /20 range, right? So 10.0.0.0 through 10.0.15.255.255 with the subnet mask of 255.255. In this case here, it's a 240.0. That's what I'll allocate to that particular location. And then I can sit there and I can break these down as much as I want to. I can start breaking that down into multiple /24s or whatever I want. So that I can start saying, okay, I have 4,096 IPs that I can use at this location, and now I can start to carve those 4,000 IPs up into much smaller subnets. And that's where doing the single allocation is going to come into play. Okay, now that we've taken a look at that, let's go. I'm probably going to have to erase this. Let me go ahead and just do that real quick. The next one's going to be the 2. Actually, I'll leave the, no, you know what? I'll leave it in play. I'll show you the 2 and how that'll come into play. Do the 255.240.0. Okay, now the 2 subnet range, that's going to be this guy right here. So, you get the argument, you don't want to waste 1,000 IPs at a site just because. Like, okay, that's fine. So here we're going to do a /21, right? And the /21's subnet is going to be 255.255. And that's going to be a .248. And then we have a /22. So it's going to be a /22's range is going to be 255.252.0, right? .00 as well. So we know we have our 2 subnet masks, right? Depending on what's going to happen. So in the first one, you would come in here, and remember, this is your range right here and right here. So the first range is going to be 10.0.0.0 through 10.0.7.255. Right? Now the next time you come in, that's going to be this is your /21 range. Your /22 range is going to be a 4 range, which means that you're going to be able to start off at 10.0.0. This will be an 8.0 through 10.0.11.255. Remember, the next range here would be 12 for the /22. So because of that, I have to take that into consideration that I can only use the 4 range in order to make that happen. So that's where that would come into play. Now I'm advertising this range and this range, a /21 and a /22. Will that work? I mean, it is more specific, yes, absolutely. But again, what happens if I have to add another 1,000 IPs? Let's say I'm growing to 3,500 IPs or 3,500 users, and now I need to scale that. What do I got to do? Well, it's simple. You just allocate another /22 to it. But what happens if there isn't, let's say 12 is not available. Let's say we've been chewed up, and let's say we're down to 128 now. We've allocated all of these other IPs. Now we're stuck, and we have to go to 10.0.128.0 through 10.0. In this case here would be a 131.255, another /22. So what happens with that? Well, I just advertise the 10.0.128.0/22 to the rest of the network, right? The drawback to this is I can't take these 3 subnets and I can't summarize them into a single advertisement. So I'm advertising 3 routes. And you're like, oh, big deal, 3 routes, not that big of a deal. Okay, well, that's fine. I mean, you don't have to be super specific if you don't want to. I'm always going to be the person that's going to draw this out and then lay out the addressing scheme before I go deploy. Because I've seen it done where people take a /16 and then they do their subnetting or they do their allocations, and then they pick a /22 out of the middle, square in the smack dab in the middle. And they have to, like this is smack dab in the middle of the range. And then you have to rip the IP addressing apart. The routing's got to get messed with. It just takes additional time and effort that you need to take into consideration when you're doing that type of stuff. So how would you summarize this? Well, in this case here, you really wouldn't be able to, unless you were to go with a 4096, and then the summary would be just a /20. You'd be able to type in, summary address. In this case here, it would be a 10.0.0.0/20 or a 255.255.240 would be your subnet mask, or whatever other range it is. So if it's further down the road, let's say that's a 16 range. If you were down in the 48 range, for example, it would be 10.0.48.0/20, and then push that range up to wherever it's got to go, whether it's out to the HQ, over MPLS, whatever the case might be. But that's basically how this works. So when you think about it that way, this is why IP addressing and subnetting is really, really important, because you need to be able to take those correlations and be able to tie them together. If you're not doing that, then you run the risk of dealing with issues down the road where you've got to rip apart a very large address block, pull a sizable subnet out, and then you've got to affect your routing. Because if you have a standard in play where you've gone through and you've got a subnet range in your EIGRP config or OSPF config that you've worked with that is basically templatized, where you just have to maybe modify some arbitrary values based on the site, the actual subnet ranges that you're going to be allocating. And then you've got to go in there and you got to rip that apart. You got to rebuild your network architecture. You've got to rebuild your subnets. I mean, at the end of the day, is it that much work? I mean, really, it's not. It's just more of an inconvenience when you've got a standard. Instead of just copying and pasting that in, you're having to re-architect things because of the lack of forethought on the design. I've seen this happen quite a few times, and it's not easy to deal with. It's actually a pain to try to wrestle this apart if you don't do it correctly. So that is why I figured it would be easy just to walk you guys through some basic design thought processes. No, I'm not getting into the weeds of how to subnet. I mean, I didn't really cover that too much. I covered how an octet works because I needed to, and the bits at the top of the octet to be able to help you understand the range and things like that. This isn't really a deep dive into IP addressing. So I wanted to more or less cover this piece because when we talk about stuff like this, let me go ahead and clear the screen. When we talk about stuff up here, eventually we'll have a very large address block. We might even have all 3 address ranges in here. I'm not sure yet. But then you might have, for example, at this location right here, might have a /18. This might be a /24. So depending on the site, may dictate the networking that needs to be associated to it. You might have a data center with tens of thousands of routes in it because you decided that you didn't want to have an on-prem data center. You wanted to put everything in a colo facility and then just pay for the services that the colo provides. And then you just have some sort of private WAN connectivity to them, internet services or MPLS VPNs or whatever it might be. So, and we'll take a look at those as well. And that's really my goal here. I can create a bunch of loopback addresses and just advertise them into the dynamic routing, and then we could simulate that as well. And that's something we'll be taking a look at that down the road. So in this video, I want to go ahead and just recap what we covered. We covered a structured addressing plan for IPv4 in this video. We'll take a look at IPv6 in a separate video, but most people are familiar with IPv4 already. I will be taking a little bit of a deeper dive into the addressing structure for v6 and diving into those details, covering the different address types and things like that, and then we'll put a plan together for that. So until next time, guys, thanks so much for stopping by and hanging out with me, and we'll catch you guys in the next video.